Hello everyone. The topic of this video is about relation between divergence theorem and Green's theorem. Before our main content, we will first review Green's theorem and divergence theorem. Now, Green's theorem. C is a curve in the plane and D is the region bounded by C. If PQ has continuous partial derivatives on an open region containing D, then we have integral of p dx plus q dy equal to integral of partial q over partial x minus partial p over partial y dx dy on D. Then the divergence theorem. So B is a simple solid region and S is the boundary surface of B. If F is a vector field whose component functions have continuous partial derivatives on an open region containing V, then we have integral of divergent F dV over V equal to F dot n ds over S. So we can see Green's theorem and the divergence theorem have similar form that integral on the boundary equals another integral over the interior. Only the dimension of boundary and the interior are different. So what is the relation between them? In fact, we can derive Green's theorem from the divergence theorem. Let me show you how that works. To reduce the dimension of the integral in the divergence theorem, we begin by choosing a specific 3D region V. We let V be the region D close 0 to A, where D is the region in the xy plane, and A is a non-zero constant. As shown in the figure, D is the base bounded by the black curve, which we call C, and V is the whole solid above it. Geometrically, this gives us a vertical cylinder. We take the flat region D and extend it straight up to height A. The reason for choosing this shape is that it lets us separate variables. The z direction is just from 0 to A, and we can clearly figure it out of the Boolean integral. That is exactly what we want if we hope to recover a two-dimensional result like Green's theorem. Now, to simplify the application of the divergence theorem, we define a vector field F equals to P of xy, Q of xy, 0. Notice that this vector field has no z component. It only lies in the xy plane. This choice is intentional. By giving it no vertical flow, we ensure that the divergence only depends on the x and the y directions. Let's apply the divergence theorem to consider the triple integral on the left-hand side. First, we compute the divergence of f, which gives us partial p over partial x plus partial q over partial y. Then we can figure out the constant a. Now, let's apply the divergence theorem to compute the surface integral on the right. We break the surface S into three parts. First, the top face at z equals a, which gives 0. Second, the bottom face at z equals 0, also 0. Finally, the vertical side surface. This is the wall formed by lifting the curve z straight up to height a. Next, we will compute the integral over the side surface of cylinder. We parameterize the side surface using r of t and z equals x of t, y of t, z, where t traces the boundary curve C, like the figure. Then the surface normal vector equals y prime of t minus x prime of t, 0. So f dot n ds equals pq0 dot y prime minus x prime 0 dt dz equals py prime minus qx prime dt dz. Finally, the integral we need equals a times integral of p dy minus q dx over z. Now, the divergence theorem reduces to a surface integral over D and a line integral around its boundary C. By dividing both sides by A, we obtain an expression that resembles Green's theorem. So not exactly, but don't worry, we are going to show next that it is indeed equivalent to Green's theorem. 好，let's G equals minus Q P, which PQ is function of X and Y, and apply Green's theorem to this new vector field. Then you will see that Green's theorem takes exactly the same form as the expression we just obtained using the divergence theorem. In summary, we've shown how the divergence theorem in 3D naturally reduces to Green's theorem in 2D through a cylinder construction. Thank you for watching.